picking up where we left off. So last time we looked at, okay, determine the partial sum. So again, writing out what you know so that you can see which formula that you need, and then, okay, substituting in and being able to solve, okay, important for that. So here's just another example. Okay, now they're giving us the sum, okay, of the geometric series. So they tell us it's geometric. Again, in this unit, like this lesson, it's obvious because we're talking about all of our geometric stuff. Okay, be nice. All right. Okay. So in this case, we're given the Tn. Okay, so we're looking at our other formula. Now, I'm just going to write them above so I don't have to keep flipping back to another page. So don't forget, for our geometric sequences and series, we're still going to be able to use the term, right, if we need to find maybe our R or T1. Okay, so we still have that formula that we're looking at. Okay, last week we looked at introducing a new formula, Rn minus 1 all over R minus 1. Okay, and then I don't think we've used this one often, which is our example right here. Okay, so now because they've given us Tn, we're going to be using the third formula. Okay, so the example number 5 was using the second formula. Oh no, we did use the third formula already. Okay. Okay, so last time we were finding the sum and substituting everything in. Now they're giving us the sum and we have to be able to isolate. Okay, so we're practicing our algebraic skills of isolating a variable, okay, when different information is given. Okay, so we're looking at this formula. Whoop, that's an odd place for it. Okay. Why will it not stick? And that just means I can't make any mistakes. All right, R minus 1. Okay, so sub in what you know, and then go ahead and solve for T1. It asks for us to determine the first term of each sequence. Okay, so we're told that our sum, okay, we have a -4 for our R, our common ratio, our n term, minus T1, okay, and then -4 minus 1. Okay. So just don't forget the order of things. Okay, so the first thing that you want to do, right, is you want to isolate your T1. Okay, but right now it's got this -5 in the denominator. Okay, so if we multiply everything by -5, okay. Okay, you with me on that one? Okay. So I can have -1,900. Sorry, 19,000, that number. And we'll multiply this out, we'll simplify that. Okay, you guys can do this on your calculators. I'm just writing out the steps here. 6, 0, 18. Okay. Okay, so I've just multiplied -4 times our Tn term. So now we have a -1. Okay, and this is your basic algebra, right? So if you were to do this, okay, add this number to both sides. Okay, we should have -1.2 is equal to -T1. Okay. I'm okay if you just, like that, you can do this part in your head, but if you need to show the steps, feel free to show me that you're dividing by -1, right, to get rid of the negative sign. I would never want this as a final answer. -T1 is equal to -1.2, right? So you definitely want to make sure that you're variable is positive with the final answer. Okay. I don't have to see this divide by 1. Like, you can just tell me T1 is equal to 1.2. Okay, I'm okay with that. Okay, but if you'd like to show it, go right ahead. All right. Okay, this time, so now we're given something different for B. Okay, I want you to set it up. Okay, instead of giving the final term, they've given n. Okay, so can we use the same formula that we just did over here? Okay, can we use this formula again, given, okay, the information that we have here in B? Okay, since we don't have the final term, this formula is not going to be very useful for us. So we're looking at using, okay, that middle formula. Okay, so write that one down, substitute your numbers in, make sure that you can isolate for T1, okay, with this arrangement of terms. Okay, so we're looking at using this one. All right. So there's 2 different ways to do this. Either way works. Okay, I'm just going to show you both ways just so that you can see maybe one's a little bit more efficient, or maybe just helps you see it in a slightly different way. Okay, I think a lot of you, okay, would look at this. Okay, or let's just clean it up a little bit. Okay, so let's do our. Okay, this we're just putting into a calculator to get some really big number. Okay, so we're multiplying by 390,624. So I just did 5 to the power 8, subtract 1, right? Okay, and then I just did 5 subtract 4, so I have, 5 subtract 1, so I have 4. All right. So just a reminder, and again, your choice. I just want to show you that sometimes there's options. Okay, so if you went this way, maybe you multiplied both sides by 4, right, to get rid of the 4. Okay, so you went 3. Okay, I just did not give myself enough space. These numbers are really big. That's the thing with geometric series, hey? Our numbers get quite large. 3, 9, 0, 6, 2, 4. Okay, this is where we're at. So maybe some of you multiplied both sides by 4. Okay. The only thing with this is that like our numbers get really large. Okay, now we're into like 1 million. Like it doesn't matter too much because the calculator does it for you. Okay, and then you're going to divide both sides. Okay, by 390,064 or 624. Okay, and that finally works down to, okay, T1 is equal to 3, right? So you can do it that way. Okay, the other option, okay, don't forget that you could simplify this because this is being multiplied. You could take it to here. Do this, the 390,624 divided by 4. Simplify that first, okay, and get 97656. Okay, and then just divide by that. Okay, so they're both the same. So this one just you're just getting rid of the division first. Okay, this one you're actually, so what I did here is I did this simplification. right? I did that divide first. Again, it doesn't matter which one that you do, but I want you to recognize that, okay, you can simplify this and recognize that it's just 390,000, right, divided by 4 to give you that number, and then you can divide out, right, in order to get your answer, okay? So either way, I just want to show you that there's some options there. All right, let's continue on. Yeah. Like here to here? Because, okay, good question. Okay, so here are some of the questions that you might expect to see. Okay, I'm on example 6. Here we go. Okay, the fourth term in a geometric series. Again, so write down the things that you know. You know that we're talking about a geometric series. Okay, and the fourth term is 30. And the ninth term, okay, is 960. Determine the sum of the first 9 terms. Okay, so in this type of question, when we don't have a T1, okay, we have 2 options. Okay, we can draw it out because we only have to go up to 9 terms, so it's still reasonable to draw this out. Okay, your other option is to set up a system of equations, right, with 2 variables and 2 unknowns. Kind of depends what you like. I'm okay if you draw it out. Okay, now you can only do this, okay, you can only draw it out if it's terms. Okay, if it gave you sums, okay, the sum of the first 4 and the sum of the first 9, for example, okay, you can't draw it out. You have to set up a system of equations in order to solve. But when you're talking about terms, okay, you have the choice. You could draw this one out. So you could do, right, this is your, okay, and we know T4 is 30. Okay, we know T9 is 960, and we know that it's geometric. So as we go from one to the other, we're multiplying by R each time. Okay, so we could say that if I start with 30 and I multiply by R times R times R, right? 1, 2, 3, 4, 5. Okay. We can shorthand R times R times R times R times R to R to the power 5. We end up at 960. Okay, we can divide both sides by 30. R to the power 5 is equal to 32. Okay, you take the 5th root. R is equal to the 5th root of 32. Okay, and R is equal to 2. Okay, so that helped us to figure out what R is, but it says determine the sum of the first 9 terms. Okay. So when we looked at, I'm just going to go back to this previous screen real quick to look at our formulas. When I look at the sum of the first 9 terms, I have these 2 choices. Okay. So either one of these, either one that I choose, I need to have term 1. Okay, so before I can use one of the sum formulas, I do have to solve for term 1. So it doesn't explicitly say what is term 1, right? So after you find the common ratio, you would then just need to take it back to your diagram, okay, back to our diagram, and remember that if I go this way in order to find term 1, okay, when I go to the right, I'm multiplying by R, and when I go to the left, I'm dividing by R. Okay. Okay, so if I know R is 2, from 30, I can go 15, I can go 7.5, and then, okay, 3.25, 3.75. Let's get my, there we go. Okay, so you could find term 1 that way. Okay, so don't forget, like use your problem solving, use your logic. And then once I have term 1, then you're welcome to, okay, use whichever formula that you like. Okay, term 1, I'm just going to say Rn minus 1. Okay. You could have chosen the other one, that's okay. And it wants us to find the sum of the first 9 terms. So when it says that not the sum of the first 9 terms, we know that n is equal to 9. So so again, here's just a little minor thing. So the formula has Sn. Okay, when you're actually finding a sum, I want you to substitute what n is equal to in this part as well. Okay, we can find our term 1, 3.75. Our R was 2, my n is 9. Okay, R is 2. And then we're just putting that right into our calculators. 3.75. Okay. I just had to chuckle because I did divide by, and then I was like, oh, divide by 1. I can do that one. All right. All right. Now, for those of you who want to see it, could we do this as a system of equations? Absolutely. Okay, let's just take a quick look at what that would look like if you totally forgot that you could draw it out like this. Yeah.
You were saying how you could use the other equation to do that question as well. But the other equation, so when you have Tn,
yep.
Tn just be substituted with T9?
Yes.
Okay.
Yeah. Exactly, because yeah, if you have if your n is equal to 9, then T9 would be your final term. Absolutely. Okay. All right, let's just pop a little. Okay. So if we wanted to set this up as a system of equations, okay, again, we have term 4 is equal to 30. Term 9 was 960. Okay, and if we set this up, we would have to be using our n minus 1. Okay, we would be using this formula in order to solve our T1. Okay, so our first equation would be, right, term 4 would be term 1 r 4 minus 1. Okay, we know what term 4 is, so 30 is equal to T1 r to the power of 3. Okay, then we could also write T9 is equal to, T9 is 960 is equal to T1 r to the power of 8. Okay, this one's like this one's not as nice because now we're multiplying. Okay, whereas before we could isolate a variable. Okay, and we could just subtract. We could do elimination by subtraction. Okay, but this one we would actually have to isolate for 1. We'd have to isolate this one. Like, it makes sense to isolate for T1. Right? So we're going to divide by r to the power of 3. So T1 here is equal to 30. Okay. Can you see why this would be a lot more work than just drawing out your terms? Okay, but I just wanted to show you that you could do it. 960, okay, r to the power of 8. Okay, so now you have 2 different representations of T1. You just say T1 is equal to T1. Okay, so you would say this is equal to this. Okay, don't forget when you have basically like 2 fractions that are equal, this is equivalent fractions. Okay, so you would cross multiply. So 30 r to the power of 8 is the same as 960 r to the power of 3. Did I do it that way? I did not do it that way. Okay. I made a little bit of extra work for myself. Okay, so here's what okay, so, sometimes we're silly. R to the power of 8 is equal to, let's go back here, 32. Okay, exponent laws, R to the power of 5 is equal to 32. Okay. So you still get to the end result, okay, but I'm not sure that you want to be doing all of this, okay, work, but you could. If you didn't know how to do it and you just remembered, when I get to terms, right, and I don't have my term 1, I can always create a system of equations in order to solve it. Okay, so it's still true, but with the geometric sequence, you have to do the substitution, okay, rather than by elimination, okay. So in that case, right, then we could just go back to our formula. Once we have R, and we just say T1 is equal to 30 over, okay, R to the power 3, which is 30 over, okay, and that's where, I guess we'd say, whoops, in fraction form, we keep it as 15 over 4. Okay, but that's where the 3.75 came in. Okay. All right. So that's why I kind of did it as an aside rather than in our notes, because I think this makes a whole lot of sense and is a lot more simple. Okay. All right. Here we go. A ball is dropped from the top of a ladder. On each bounce, the ball reaches a vertical height that is 3/5 the previous height. Okay, so we can also put in the word here of 3/5 of the previous height. We remember that of means multiply. Okay, so this is actually telling us what our common ratio is. Okay, our common ratio is 3/5. So it's getting smaller and smaller each time that it bounces. Okay. Determine the total vertical distance traveled by the ball when it contacts the ground for the 6th time. Okay, I'm really going to stress this. Draw it out. Okay, because so you have a ball. Okay, and I know that the ball is probably bouncing vertically, but I'm just going to draw it out to show that it's got a little bit of horizontal distance as well. So the ball drops. Okay, and it bounces. Okay, 3 times, 4, 5. Well, I guess it gets smaller. Okay, 6. It wants to know vertical difference after it contacts the ground for the 6th time. Okay, so 1, 2, 3, 4, 5, 6. So what we're interested in, okay, is this ball. Okay, notice that the ball goes up and the ball comes down. Okay, so this was kind of like that tree question where the person had to like walk out to the tree but then walk back to get the next one. Okay, so it wasn't as simple as saying, I'm just going to use that term. You still have to figure out what some of these are. So for example, okay, my pattern, okay, so I start at 25, right? 25? Okay, so I start at 25. Okay, 1, 2, 3, 4, 5, 6. All right. So I start at 25. Well, okay, let's just say this for a sec. I start at 25, but, okay, this is kind of outside of my situation because what I'm interested in is going up, coming down. Okay, do you see that this is only the coming down part? So if we actually consider that at the end, okay, let's look at this pattern. So if I start at 25 and I do 3/4, okay, how tall is this, how high is this bounce going to be, this one right here? Okay, so we do 25 times 3/4. Okay, did you get 15? Okay. So, but it's 15 up and 15 down. Okay, so after the first bounce, okay, I'm just going to write this here. Okay, it went up and it went down, so that's 30. Okay, this height, okay, every time that we change heights, right, we're multiplying by 0.35. So then 0.35 times 3/5. Okay, so this one's 9. Okay, because each time I'm going this way, I'm multiplying by 3/5, right? Okay, so I'm at 9, but I go up, I go down. Okay, so my total, because it's asking for, so just make sure that when you're drawing your diagram, you're seeing what it's asking for. It wants the total vertical distance traveled. Okay, so you found the height. So this one, what I want to point out is the height, okay, is not your term number. Okay, the distance traveled is your term number. Okay, the height is part of it. You have to figure out the height in order to figure out, okay, the distance traveled. Okay, and then 3/5 of 9. Okay, so multiply that by 3/5, so 5.4. Okay, we go up, we go down. So now we're at 10.8. Okay, the next height. Okay, 3.24. Okay, we go up, we go down. So we're at 6.48. Okay. We go up. Okay, we go down. Didn't need that one. 6.48 and then 3.88. All right. So this is our this is our term 1, our term 2, term 3, term 4, term 5. So when we use our sum, okay, let's use we're looking at, so we can use, yes.
I'm just confused why we have it like shifted over, like with the 9 on top of the third bounce. Wouldn't the 18 be to the right? Like why is it to the
Oh, I didn't space it out right perfectly. Yeah, you're right. It should be under each one. So with this one, similar, yeah. Probably. Yes. I had 3 decimal places on my sheet, that's why. Okay, so this is similar to that question. Remember that thinking question we had with the salary? Okay, that you could use the sum up to a certain point, right? Remember with the salary question, the person got the raise for the first 10 years. And then after that, the raise stopped. So we could use the sum formula for the first 10 years, and then we kind of had to manually do it. So this one, here's the pattern. We still have this 25 that we've kind of just set aside for now. This pattern, we can use the sum formula on, and then we just add that. Then we add the drop at the very end. Okay, so because this isn't an up and down, this first one here is not part of the pattern. Okay, the pattern is up and down, up and down, up and down. That's the pattern. That's why this one here, this up and down, that's why that's our T1. Okay, 25 is not our T1. Okay, we'll deal with 25 in a moment, but just for us to be able to use the formula, we just had to shift everything over a little bit. Okay, so when we're looking at the sum of the first 5 terms, okay, so it was after the bounces, okay, then Okay. Our first term was 30. Our common ratio, right, was 3/5. Okay. Oops. Let's fix up my formula. All right, and then we have 2 to the power of 5, subtract 1, okay, all over 3/5, subtract 1. Okay, we put that into your calculator. Okay, calculator can do all the work. These are just numbers. Okay, so as long as you're inputting it correctly into your calculator with brackets or using the stack fraction feature, okay, you should be able to get to, okay, 69.168. Okay, now, okay, we're going to add the 25, okay, from our first drop. This is the drop height. Okay, and then that gives us 94.168 meters. Okay, and this one, because it's word problem, yeah, we would just stick in a nice sentence answer. Okay, so the total vertical distance, okay, traveled by the ball, okay, let's just round that nicely, 1.7, that's fine. Okay. So this one, right, that one takes a little bit of brain power. Okay, so I would go back over that one, okay, draw it out until like you're solid with it. Yeah.
If you already figured out all the heights of bounces, couldn't you just add those up?
Sure thing. Yep, absolutely. Could you not have just done this? Yeah. Okay, and then you would do your 25 plus as well, right? Yeah.
That just seems like
Less work.
less work, possibly.
Yeah, absolutely. Okay, so don't forget you can always do that, especially with only 5 terms, 6 terms, right? For sure. Yes.
Do you want it in decimal or fraction?
In this case, because of the context of it, I'd be okay in either, because they give you the, so the question is decimal or fraction, okay? Because they do give you 3/5 as the common ratio. So if you gave me the answer as a fraction, awesome. Okay, that is a more accurate answer. However, in the context of measuring things, okay, like we would probably say, right, 94.1 meters rather than calling it a fraction. Okay, so in that case, okay, I would be okay with either. I did it all in decimals. I'll have to, okay. So this, okay, so just another little note to self that I have, okay. Okay. So this is different, okay, than just the rebound height. Okay, after 6 bounces. So just write a note to yourself. Okay. So in this particular, they might give you either or kind of questions. They might ask you, what is the rebound height? Okay, in that case, they're looking for this number. Okay, just the rebound height. Okay, they're just looking for the term number. But if they want to know the combined vertical height, it goes up, it goes down. Okay, that's how the sum would work. If they just want the rebound height, that would be a term thing. Okay, so then in that case, right, yeah, this would be term 1, term 2, term 3, term 4, term 5, term 6. Okay, if they just wanted the rebound height. Yeah.
How come last time we did it from 17?
Because, so that's a great question. If it wanted, okay, the rebound height after 6 bounces, yeah, you'd need term 7. Okay, so that's why this is different. It just wants the total distance traveled, okay, after, like, once it has bounced the 6 times. So it's not wanting that extra little bit. Okay, that's a really good distinction. Yeah. For this one, no. For the distance traveled and on the 6th bounce. Okay. For the other one, if it says what's the rebound height after the 6th bounce, yeah, it wants that 7th term. Great question. Yeah. Okay. Okay. Oh, here we go. All right. So we are going to introduce, okay, the next lesson. We'll get started on it today. We'll finish it tomorrow. Okay, we'll have a little bit of time for some review tomorrow. Okay, and then we'll be gearing up for your first unit test and also be brushing off our skills to get ready for our unit in quadratics. Okay, so just jot this down. Okay, I'll give you some time at the end of class. Okay, we're going to have those 5 questions for homework. Okay, I'm just going to introduce the next topic and then we'll circle back and do some of the homework questions. Okay. All right. Take a quick stretch break if you need to. Okay. All right, our final topic, okay, is simply a special case of a geometric series. Okay. Okay, we are going to be looking at something called the infinite geometric series. And yes, this is where you get to use infinite, okay, the infinity. Mine looks a little lopsided, okay, it's supposed to be this, oh, that's even worse. It looks like an 8 on its side. However you can draw it is fine, okay. Mine's a little flattened, it's okay. That's the infinite symbol, okay. So what happens, I don't know if you've noticed, okay, as we were doing some of these questions, okay, but sometimes, right, our geometric sequence, right, when things, like when our common ratio was like a large number, or like even if it was 2 or 3, okay, the series would like skyrocket, right? It would look like this, okay? It would be exponential growth, right? And so what happens is we could actually never find the sum of the series. Like we always have to like pick a number, the sum of the first 10 terms, the sum of the first 20 terms, right? It might not even make sense to say the sum of the first 100 terms because the number would just be so large because it diverges. It just keeps getting bigger and bigger and bigger, okay? So that's what the definition of a divergent series is. Okay, it just keeps on growing. It's an exponential growth, okay? And it looks like this. So we would just need to have an actual number to pick. However, okay, maybe you noticed that when the common ratio was like a fraction, okay? Maybe it was like a half or a third or something like our ball bouncing, okay? Eventually, the bounces of the ball get smaller and smaller and smaller and smaller until they're like practically 0. Okay, consider myself and the wall. Okay, if I were to cut the distance in half, okay, I would now be here. If I were to cut the distance in half again, I'd be here. If I were to cut the distance in half again, now I'm here, half again, now I'm here, half again. Am I technically ever going to touch the wall if there's always half a distance between me and the wall? Technically, no. Okay, but once I get like close enough, like I'm touching the wall, guys, like the space between us is so minute, okay, that there comes a point where we say, you know what, it's close enough to 0. Okay, that's what we call a convergent series, where the number gets so infinitesimally small, okay, that it practically becomes 0, and our series actually ends up with a number, okay? So you have this in your notes, okay? A convergent series, okay, approaches a fixed value, okay? So what does this look like? Okay, let's just do a picture of this first, and then that way you can kind of visualize it as we talk about it, okay? So you'll see here this piece of paper. Like say we took a piece of paper and we folded it in quarters, okay? And then, so that's what this is. Okay, we took we folded it in quarters. And then from that, we folded it in quarters again. So now you have this smaller area, and then we folded it again, okay? And again, until it like gets really, really small, okay? So what we're doing is we're taking, okay, a number. So we started with 1, actually, okay? And then we multiplied it by a quarter. Okay, and then we multiplied it by a quarter, multiplied it by a quarter. Well, like it's getting like really, really, really small. But take a look at this picture, okay? And if I were to color it, okay, to me it wasn't glaringly obvious to me. Maybe you guys can already see this, okay? If I take this portion here, okay, all right, and then I just switch colors. So here's my gray boxes. I've got some blue boxes, and I've got some green boxes. Okay, do you notice that like all my boxes are the same size? Okay, so I have, okay, 1 gray box, 1 green box, 1 blue box. So what proportion of the diagrams appears to be shaded? Okay, 1 out of the 3 of them. So this particular, and I think it continues on this page here, so they kind of did white, gray, and black, okay? This particular series that we keep going down by a quarter, a quarter, a quarter, okay, eventually, okay, it's always going to be a third of the whole, no matter how many iterations you take. If you were to use your calculator, right, and you were just to like multiply like by 0.25, 0.25, 0.25, 0.25, eventually your number would just get closer and closer to 1/3. It would converge on a fixed value, okay? And that's what we're going to be looking at, okay? Because it converges, we can do, I would consider it a little bit of a shortcut, okay? We just clean up one of the formulas for this special case. So of course, before we can use the formula, okay, we always have to check, is this the special case? Can we use the formula? And if the answer is yes, like, so we check, does it converge or does it diverge? If it converges, then we're allowed to use the formula. So what formula, you might be asking? Okay, so here is the original formula that we had, okay? And what happens is, okay, for values of r between -1 and +1, okay, so that means all your, like your fraction values, your decimals, right? So like 0.35 or, you know, 3/5, okay, -1/2, right? Kind of between those numbers. If it was greater than 1, right, that would be growth. Okay, if it was like 1.2, so just because it has a decimal doesn't mean it's convergent. It has to be less than 1. Okay, so, whoop, I'm still on highlighter. That's okay. Okay, sometimes you might see, okay, I don't know that we talked a lot about absolute values last year, okay, but you might see this in your textbook. The absolute value of r, okay, is less than 1. This just means, with the absolute value, it just takes off the signs, right? It just means that r, okay, is between -1 and 1. Okay, so if you see this absolute value bar, this is what it means. Okay, so just so you know where it comes from, because some of you like to kind of know, okay, well, we have this new formula. Why does it work? Where did it come from? Okay, so you don't have to prove the formula or be able to derive where it came from, but just so that you know, okay, when we use this formula, okay, you can see as n gets very large, okay, when r is between, like when r is a decimal or a fraction between -1 and 1, okay, like let's say you had, okay, 1/2 and you did that to the power of 20, Okay, what do you get? Okay, if your calculator's like mine, let me pull up mine. Oh, I don't have it open yet. Okay, my calculator is not there. Give me a sec. All right, so my example was if I did, okay, oh, 1, oh, don't be mean to me right now. Okay. Okay. 4 divided by 8. Oh, never mind. Okay. There. Okay. I don't know what's going on with this thing. Just give me my normal thing. I don't know what's going on. There. Okay. We cleared it off. Oh, we don't even want to be in there. Okay. Back to my example. So 1 divided by 2. Where's my... okay, guys. 0.5 to the exponent 20. There. Okay, so you got that. Okay, and you're like, what is that? Okay, so don't forget, maybe you haven't taken the sciences quite yet. Okay, but this is basically saying that you have to multiply it by 10 to the negative 7. So you got to start from here and move the decimal place over 7 to the left. Okay, so that is 0.000000095. Okay, which is like a pretty small number. If you kept going, right, 0.5 to the exponent 50. Okay, now we're moving the decimal place over 16. So you can see that when you take a fraction 1/2 and you put it to a large, like a large exponent, it basically becomes 0. It gets so infinitesimally small that it becomes 0. Okay, so that's why, so this part right here, okay, is becoming 0. Okay, so when that happens, right, you can just substitute 0 in for it. Okay, and you end up getting this, right, this T1 negative 1 over R minus 1. Well, that, like this is a little awkward, okay, to have a negative T1. So all they did was they just pulled the negative out of the top and the bottom. Okay, so if we pull a negative out, they have the top, and if we pull a negative out of the bottom, we end up getting negative R, okay, positive 1. Okay, our negatives would cancel with each other, and then we would just rewrite this as T1, 1 minus R, because negative R plus 1 looks weird, so we just can rearrange those. So that's what this is. Okay, this is our beautiful new formula that we can use. Look how simple that is. Okay, we just take the term 1 and we divide it by 1 minus the common ratio. Okay, so we can use this. This is an infinite sum. Okay, it only will work if your common ratio, right, is within the parameters, if it's less than, okay, or, sorry, if it's greater than negative 1, less than 1. Okay, if it converges, then we can use this quick formula. Okay, so for example, okay, they're just going to take us through. State whether each infinite geometric series is convergent or divergent. So you look at this, you look at R. Is it convergent or divergent? It's divergent because R is 4. R is a big number. So you're looking, this is what it would look like. It would look like this. Okay, so this is divergent. Okay, so that means that we can't use this formula. We would have to use the regular sum formula that we've been doing for the last few days. Okay, so this one's divergent. We wouldn't do anything else with it. Okay, how about this guy? Okay, all you have to do is just look at the common ratio. Does it fall between negative 1 and positive 1? Absolutely. It's a fraction. Okay, it's a proper fraction and it's negative. Okay, so because of that, we would say this is, so that yes, this is convergent. So we can now use, okay, we can now use that sum formula. All right, this one, the same question, they're just making us do a little bit of work, okay? So in this one, we have to figure out what the R value is. So don't forget, you can always take term 2 divided by term 1, 25 divided by 1 over 25. Okay, 1 over 5. Convergent or divergent? It's a fraction. It's convergent. Okay, so that's what you would do. You would first check to see whether it's convergent or divergent. Okay, and if it is, that's when we can use this infinite sum, okay, formula. Yeah.
On that, so some formula, though, it's a common ratio only if 0 is, if R is between 0 and 1.
Yeah.
What is this one?
Yes. Okay, so I don't know why they only have that. Okay, if it's a negative common ratio and it's a quarter, yeah, same thing, because this is really what we're after. Okay, I don't know why it has that. It's this one.
So you don't have to reverse the formula at all.
Nope. Nope, not at all. Okay, if it is negative though, and you use the formula, okay, this one might be negative, so let's give this one a try first. Okay, let's figure out our common ratio. Okay, so term 2 divided by term 1. Oh, it's not. This one's still positive. Okay, 2. Okay, so this is, okay. Before I lose it, I'm going to write it down here. Okay. So say, for example, like the question that you just asked, say our common ratio was -1/4. Okay, when we use the formula, okay, so our new formula, T1, 1 minus R. So don't forget when you sub that in, whatever your T1 is, let's say it was like 18, okay, 1 minus negative. Okay, so you still have to keep the, if it's a negative ratio, still have to keep it. So don't make that little mistake where you just put in the minus, okay? You would still have to add this. So it would be, 18 over, right? 1 plus 1/4. Okay, so yeah, so that's kind of the thing to be aware of. You don't have to rewrite anything. You just have to make sure that you don't mess up on the double negatives there. Okay, that was just a little aside. Okay, what I would like for you to do, I'm going to stop there. Okay, we're going to finish up this lesson tomorrow. Okay, I want you to grab a textbook, circle back, do those questions from the end of this lesson. Okay, you have 5 questions. A, 5B, 6, 7, A, B, and 10. Okay, and then if you have anything to show me, okay, homework, if you have questions, okay, about the 10 a week. Okay, a few of you haven't picked up the 10 a week from Thursday. Maybe you were away. I do have a couple here still. Okay, you can come and pick those up. Okay, those are great things to be doing in preparation for your unit test. Okay, come talk to me. I will find you if I have something that I need to talk to you about. All right.